All right, so now we're going to get started with section 9.4 LaGrange multipliers. So this is going to kind of take us to the next level of more optimization-based problems and figuring out how we want to do that and everything. So the method of Lagrange multipliers to find a maximum or minimum value of a function f of x, y, subject to some constraint g of x, y equals 0. So this is heavily business oriented. You're going to end up doing this later on in your upper level business classes as well. So we want to form this new function, capital F of xy lambda. So that's going to be equal to our original f of xy function they gave us minus lambda times our constraint. Now always make sure that your constraint is equal to 0 before you try and do this minus lambda times. So our lambda variable there is called a Lagrange multiplier. This is like our um, kind of like a little fluffer in a sense. It's just a little multiplier that we have to kind of worry about here. So once we form our new function, we need to find all of our first partial derivatives, f sub x, f sub y, and f sub lambda. We're going to end up solving our system of f sub x equal to 0, f sub y equal to 0, and f sub lambda equal to 0, normally by taking f sub x and f sub y and solving for lambda. So in other words, we're going to take these two right here, and we want to solve for lambda. Then we're going to take that and plug into, by doing that, we will end up getting a relationship on x and y that we can plug into the f sub lambda one. So if we let a, b, and lambda represent the solution of this system, we normally must determine whether a, b, lambda yields a maximum or minimum of the function. For the problems in this text, we will specify that a maximum or minimum exists, and therefore that's actually what we're going to be finding every single time. We can have functions of 3 or more variables. Normally, we're going to end up using 2 plus lambda, and that'll be it. So we're told, find the maximum value of a of xy equals xy, subject to the constraint of x plus y equals 20. So first note that we need to solve our constraint to set it equal to 0. So we get x plus y minus 20 equals 0. And therefore we can form this new function. F of xy lambda is equal to xy minus lambda times our constraint of x plus y minus 20. This is going to be our function that we're going to work with for the remainder of this problem now. So the first thing that we're going to do is we need to find our all three of our partial derivatives. F sub x is equal to y minus lambda. F sub y is equal to x minus lambda, and f sub lambda is equal to minus of x plus y minus 20. Now let me go back for 1 second just so I can get this function. So we have xy minus lambda times x plus y minus 20. Another way we could write this is xy minus lambda x minus lambda y minus lambda times 20. So if we were to write it that way, with respect to x, we get y minus lambda. Fy is x minus lambda. And f lambda is minus of the x plus y minus 20, which is just minus x minus y plus 20. So, yes, I know it says we're going to set each one of these equal to 0. The easy way to go about this is y minus lambda means lambda equals y. X minus lambda means lambda equals x. Putting these two together, we get x equals y. By putting these two together, we can then plug into the next equation, which I'm sure we're fixing to do on the next slide here. So that's where we get this x equals lambda, y equals lambda. So we're going to substitute that x equals y or y equals x into the third equation from the previous slide. So we get x plus x minus 20 equals 0, or 2x equals 20. So x equals 10. So if x equals 10, then y equals 10 because y equals x. So therefore, plugging back into the original function, a of 10, 10 is equal to 100. So in a lot of cases, we're not trying to find what lambda is. It's just more of a placeholder. By using this piece right here, x equals lambda equals y, actually in this case, we found that x is 10, y is 10, and lambda is 10. That's not always going to happen that we're going to end up with all three of them being the same exact value. In fact, I'd say most times it will not. So we're told, find the maximum value of f of xy equals 3xy subject to the constraint 2x plus y equals 8. So if we rewrite our constraint, we get 2x plus y minus 8 equals 0. And we have the new function f of xy lambda is equal to 3xy minus lambda times 2x plus y minus 8. So very similar to the one that we just did a minute ago. Just now we're using it with this new function. It's the same setup. So we end up with 3y minus 2 lambda is f sub x, 3x minus lambda is f sub y, and negative of 2x plus y equals 8 gives us f sub lambda. So using that same theory as before, the second equation down here can give us lambda equals 3x. So therefore, let's take this lambda and let's plug it into the first one. So we get 3y minus 2 times 3x equals 0, or 3y minus 6x equals 0, 3y equals 6x, y equals 2x. So with y equaling 2x, we can then take that and plug it into the third equation. So when we get this y equals 2x, which is what I just found on the previous slide, we can then take that and plug it into the third equation. So we get 2x plus 2x minus 8 equals 0, 4x equals 8, x equals 2. Now, since y equals 2x here, we take our x equals 2 and we plug in, and that's where we get these values of y equals 2 times 2, which is 4. The maximum value of subject to our constraint occurs at 2, 4. So f of 2, 4 was 3 times x times y. So 3 times 2 times 4 gives us a maximum value of 24 for this type of problem. So here's a more involved piece here. That's more of an engineering style problem here. So it says the standard beverage can has a volume of 12 fluid ounces or 21.66 inches cubed. What dimensions yield the minimum surface area? We want to find the minimum surface area. Assume the shape of the can is a right circular cylinder. That just means it's a circle. It looks like, and it's just a standard shape of a 12-ounce can. We want to minimize the function s given by the following. S of h comma r is equal to 2 pi r h plus 2 pi r squared. Keep in mind, pi is a number. It is not a variable. Only h and r are the variables here. Subject to the volume constraint, pi r squared h must equal 21.66. Or in other words, pi r squared h minus 21.66 equals 0. Pi r squared h is just simply our volume, which we were already told what it was in the beginning. So our function becomes S of h comma r comma lambda is equal to 2 pi r h plus 2 pi r squared minus lambda times pi r squared h minus 21.66. Taking our three partial derivatives, S sub h is 2 pi r plus or minus pi times lambda r squared. S sub r is 2 pi h plus 4 pi r minus 2 lambda pi r h. And then S sub lambda is minus a pi r squared h minus 21.66. So to solve for lambda, the easiest way to do it is, we're going to look at it on the next screen. So setting those three equal to 0, since pi is a constant, if we look at solving the first one by setting 2 pi r equal to lambda pi r squared, if we divide each side by, so we're solving for lambda, so we're going to divide by pi r squared in each case. By canceling out, pi is a constant, so we can cancel it out. R over r squared gives us just division by r, so lambda equals 2 over r will be our substitution factor piece for that one. By substituting this in to the second, since r is not equal to 0, cannot be a solution to the problem, we will continue, because if r equals 0 was a solution, we would be in trouble because we would have division by 0 in that last piece, and we couldn't have done that. So if we solve that, so from the previous one, we had that lambda was equal to 2 over r. So since lambda is equal to 2 over r, what we're doing here is we're not substituting 2 over lambda. That should be 2 over r into the second equation. So when we substitute that in for lambda, we get 2 pi h plus 4 pi r minus 2 times 2 over r times pi h. The r's will cancel out there. So we're left with 2 pi h plus 4 pi r minus 4 pi h. So by doing some math, this would give us 4 pi r minus 2 pi h equals 0. So that means that 4 pi r equals 2 pi h. That means that r, actually we're going to solve for h. H equals 2r. We could have solved for r as well. It just would give us a fraction that we don't want to have to worry about, so we want to make it easy. So h is equal to 2r. So therefore, we are going to plug into our third equation. So we get pi r squared times 2r minus 21.66 is equal to 0. So then we get 2 pi r cubed equals 21.6, dividing each side by 2 pi. So when we divide each side by 2 pi, 21.66 divided by 2 gives us the 10.83. The pi is still down there. So we get r cubed equals 10.83 over pi. Taking the cube root of both sides, we get r is equal to the cube root of 10.83 divided by pi, which is approximately 1.51 inches. Therefore, when r is equal to 1.51 inches, h was equal to 2r. So this was 2 times 1.51. And the surface area is then a minimum and is approximately, if we plug back into the original function, 2 pi r times h plus 2 pi r squared. Plugging that into our calculator, we should get approximately 42.98 inches squared as the minimum surface area. So again, LaGrange multipliers are a little bit long and they are algebra heavy, But in terms of the process, it's the same exact process every time. Take the function they gave you, subtract off lambda times your constraint, find your three partial derivatives, fx, fy, f lambda. Excuse me. In general, take your first two, solve for lambda, set them equal to each other, get a relationship on x and y, plug that relationship into the third equation to solve for one of your variables, then take that one and solve for the other variable, and then plug both your variables back into the original to get your minimum or maximum value, depending on what they're giving you.